practicing more of sequence processing. So here now in the string problems in the Python examples. So we have various functions operating on text string conversions. So here first the function. Remember again, all the Python strings are immutable. None of these functions never modify the string that they're given. They just build up a new result and return that one. So here a function that is used to title case all the words inside the string. So this is again a situation where processing the current character depends on the value of the character, but also the value of the previous character. So again, this technique that we saw earlier, maintain a separate variable that log steps one step behind after our loop variable. So a prev initially, so we can pretend that every string there is like an invisible space before the first character. This way we reach the blessed state that inside the loop the processing for every character in the string is identical. We don't need to extract the processing of the first or the last element as a separate thing. So pretending that every string is preceded by an invisible space. If we pretend that it exists and accordingly, so then it is as if it existed. So if the previous character is a space and the current character is not a space, so Unicode has a bunch of white space characters, more than most people would expect. I don't know how many this one recognizes. I once tried it with the Wolf from Mathematica. I think it recognized 16 or 17 of them. Okay, so then result is gonna be the character converted to title case. Technically this is not the same as the uppercase, but that's for some linguists to explain, so I wouldn't know. Then what the important thing that I do know is that in this particular pattern, so when prev is your previous element, so having processed the current element becomes the previous element for the next round. Next round C is gonna be the next element, but the prev is still the one step behind, and return the result that was built up. Here is another problem. So the sequence now again, so the decision, so we cannot do this with the list comprehension converting back and forth because the processing requires the previous character also. So list comprehensions are not good in maintaining any kind of a state information between the things. So they implicitly assume that the processing of every element is totally independent of the other. So theoretically list comprehension could be arbitrarily parallelized, but that's gonna be another science fiction thing. Although we live here in the past science fiction universe and nobody has noticed, but let's see what we have here. Things that would seem magical. So previous character, now we say that there isn't one, so none isn't a problem because the inequality comparison doesn't care about if this is none, it does the right thing. So result empty string, so where we build up the characters. So how do we recognize a duplicate character? So one that is not, so the one that is not is one that the previous character was something else. So notice that this version of the problem, two different versions, the other versions next. So this one requires the goldfish level of memory, just remembering the immediate previous character, but none before. So the same character can be appearing in the result multiple times if there is some other character in between. So now this next version, so this one I use because it's a good thing we get to use a set in here, set of the things that we have seen. So we remember we have the entire Unicode potentially coming there. So we cannot just assume that these are all like the first ASCII characters or similar. So that kind of thinking should have gone away decades ago. So result, empty string again. Notice the multiple assignment to save the vertical space. And the things that we have seen is an empty set. So every time we see something, so then we add it to the set to remember we have seen that before. Now looping through the individual characters of a string. So a string is a sequence of characters. So looping through it gives the individual characters. And if the character is one that hasn't been seen so far, not in scene, so then result, so add the character to the end of the string, and then add it to the things that we have seen. There's no law of nature or man saying that you cannot, in a seemingly redundant fashion, maintain the same data in two different data structures. Notice how the result string and the scene set contain the exact same characters, but the scene makes it much faster to check whether we have seen a character already. Otherwise, we have to look at every character in the result before we can say no. So running through this unique characters of my name, so end up being this one. Notice that the uppercase and lowercase versions of the characters are different characters, and white spaces are characters like any other character. White space, just no pixels happen to be turned on if it gets printed. And one more, let's do it before we go to the next half in the next lesson. So testing whether two strings are anagrams. We're gonna be doing this in an even more clever fashion later for a speed up multiple test, but so if two strings are anagrams, contain the exact same letters with the exact same multiplicities, so therefore if the words are a different length, that's it, so no need to perform an expensive test that realize that it couldn't have worked. And then so anagramness, so this becomes a lot easier once we sort both of these strings. So the sorting for two anagrams, if you think about it, should produce the exact same result. So if the two sorted versions of the strings are different, so therefore there's gonna be one has a character that other one doesn't have, or at least in a different multiplicity.